Good evening, all of you. I welcome back to day 2 sessions of online FDP program. And today we will have back-to-back 2 sessions. The first session is running from 6 p.m. to 7:30 p.m. and then we will have 2 minutes hardly break. And thereafter 7:30 to 9 p.m. we will have second session for today. I hope your 3 hours time would be justified with the resource persons we have today. And without any late, I request Dr. Kelly Durga Prasad, Assistant Professor, Mechanical Engineering Department, to give brief introduction of Dr. Neeraj Sharma Garu, and followed by his session. Thank you. Over to you, Dr. Kelly Durga Prasad.
Thank you, Dr. Santosh, for giving me this opportunity to coordinate this session. And good evening, all. I am Dr. Kelly Durga Prasad from ADITYA-TKL-MECH and Management, and I am here to introduce our research person, Dr. Neeraj Sharma. He was a distinguished associate professor at NIT Agartala, and his primarily research interests are composites, biocomposites, biomaterials, and porous alloys. He has been recognized among the top 2% of the influential scientists, scientists in the world, as published by the Stanford University, USA, and elsewhere from 2022 to till date. So continuously, he was the top 2% of scientists from last 3 years. Dr. Sharma has begun his academic journey with a BTech in Mechanical Engineering from Kurukshetra University in 2006, followed by MTech in Mechanical Engineering from Maharshi Markandeshwara University, where he was awarded a gold medal for his academic excellence. Later, he completed his PhD from YMCA University of Science and Technology in 2017. With over 15 years of academic and industrial experience, Dr. Sharma has held various positions, including professor and associate professor at Maharshi Markandeshwara University and technical associate at Tata Motors. Later, he joined NIT Agartala as an associate professor in leading research and academic initiatives in mechanical and production engineering department. A prolific researcher, Dr. Sharma has authored more than 102 research articles published in reputed journals, along with 4 book chapters and 24 conference proceedings. His work was garnered over 2040 citations, reflecting the significant impact of his research contributions with an H index of 26. And his publications demonstrate high relevance and value in the scientific community, with some of his notable research works on enhancing the K-means algorithm for data mining and development of optimized neural network models, and also on the evolution of reinforcement learning and its applications. Dr. Sharma has received multiple accolades for his contribution to research and academia. Now he is actively involved in guiding doctoral researchers with recent theses focusing on machinability analysis of carbide tools during sustainable machining of inconel alloys and additive manufacturing techniques, along with the control of shrinkage porosity in green sand casting of automotive parts. Dr. Sharma is a life member of ISTE and associate member of IE. His dedication to research, teaching, and innovation continues to make a profound impact in academia and the broader scientific community. And once again, I am privileged to introduce Dr. Neeraj Sharma because I am also one of the MTech research scholar alumni from NIT Agartala. And thank you, Dr. Sharma ji, for sharing your impressive background with us. And I just request you to take over the session. Thank you so much, sir.
Thank you, Durga Prasad ji, for this nice introduction. First of all, am I audible?
Yes, sir.
Okay, fine. So I don't think so that this introduction will take more than 1 or 2 minutes, but you already give 4 minutes of introduction. So first of all, thank you. Now I'm sharing my screen first. Is it visible? Hello, is it visible?
Yes, sir, it's visible, sir.
So I think the audience, maximum of the audience is from the faculty side. or maybe there are,
Can you make it as a PPT?
you are the research scholar of
Slideshow.
PhD, I think so. So whether I maximum faculty, or if there are some researchers who are working towards the research side, either they are PhD scholar or postdoctoral scholar, or maybe they are master. Everyone has to do some kind of research, even if they are a faculty member from some institute. In that case, they also wants new perspective of the research. So in my presentation, I just put just the classification and starting as a just like introduction of additive manufacturing and then its classification. But finally, I had 1 or 2 case studies of research, so that you can get some idea that how can we go if you have some 3D printer or fused deposition modeling equipment at your institute. So you can do research in some way. But basically, as my research area is concerned, my research area is related to the biomaterial. First biomaterial, then composite material. So it is somewhat related to the material science. So how can we do that research with the help of additive manufacturing? Till now we heard about, I think there are 2 types of manufacturing. One is additive manufacturing, another is subtractive manufacturing. Just like the next, just, okay, fine. So there are, if this one is our product, we want to manufacture this product, so we can go by different means. So in case of manufacturing, we want to convert the raw material into the finished good, which is, I think if you are a faculty member, you definitely teach your students to this definition. If you are a PhD scholar or a master, then you definitely read this in our conventional book, that converting of raw material to the finished good, that is our manufacturing process. So how can we achieve the conversion of the raw material into the finished good? So there may be 4 methods. First, we take this part and we do different kind of machining operation, just like on a shaper or maybe lathe machine. We do some kind of machining, and finally our final product is this. In second, we may join 2 different parts, first and second, and with the help of this joining process, we can convert the raw material into this. If we give it first number, so we can convert with the help of joining this part. So these are some basic thing. So in case of forming operation, we have some kind of die and we press the material, and finally the shape is final product we can get. The fourth one is layer by layer manufacturing or additive manufacturing, which basically today's topic is. So in this case, this final product can be manufactured if we put some kind of layer here, and final product will be of this shape, first number. Okay, so we can develop one part by different means, by different methods. So in traditional process, when this one is our material, we do subtractive type of manufacturing, means we are basically reducing the material, some kind of machining it will take place, either it is drilling or shaping or some lathe machine, and final product is this 3D object we get, and the wastage which is involved for the development of from this material to this shape, this one is the waste material. So we do lot of machining, lot of energy we use. Okay, one thing I also want to clear, that if you have any doubt, so please don't wait that we will ask our question at the end. Means there may be some 10 or 20 minutes of question answer round. You please unmute yourself and ask me in between that in between the session, because that will be good. Otherwise, after every I am going to the second slide now, third slide or a fourth slide, you just ask in between that session. That will be fine. Or maybe few questions we will take in at the end of the session. But still, session is open at every time. You can unmute yourself and ask me at any questions. Okay. So this is our traditional manufacturing method. That if we want to change this material to this product, there is lot of wastage and lot of energy we have to use. Their energy, manpower is mandatory. Energy is second point, that we use some kind of electricity. Then third one is at least we need tool. So these, in traditional process, these things are involved. In the additive manufacturing, we have this material in the powder form, okay, and powder, or we can say that in paste. So with the help of additive manufacturing, there are maybe some laser, maybe some nozzle, and but layer by layer method, we can develop this product. So definitely we cannot say that the product is its final product, but we need at least some post processing. Post processing means there are maybe some burr present or here, or the accuracy is definitely, you will get a good accuracy, but still if there is some burr or some kind of finishing operation you want to perform, then the waste is this material. So most of the time we say that if we talk about not 10 to 15 years back, so additive manufacturing it was not commercialized at that time, but nowadays it is very much commercialized. But there are few methods still. There are few methods we are not able to commercialize due to the cost involvement. Just like suppose at your institute, at most of the institute in India, you can find out, okay, additive, we have the rapid prototyping or 3D printer we have in our institute, at your institute also. But those 3D printer are of, they can develop plastic part, not the metal part. So today at the end, I will discuss this thing, that how can we develop the metallic part if you have some plastic printer at your institute. So in that case, we will discuss this thing, because I think that will be better point if you want to go towards the research side. Okay. So just now this additive traditional and this additive manufacturing type. So additive manufacturing. So this one is additive manufacturing involved. We can say that it is a layer by layer fabrication of three-dimensional object. Just like in this picture, I'm showing just the picture. So there is this is basically the surface, sport surface we can say, and this one is our nozzle. Some material maybe in powder form somewhere else, and it comes through the input, and that material is printed here. But before that, we have to, what design we want. So we have to make some kind of design, either that is a CAD model. Then first CAD model, we convert that CAD model into the STL format, just like this type of thing. So finally, with this printing technique, or final product will be manufactured. Similarly, in the second, you can, this one is we want some kind of shape here, and we can, with the help of some laser, we can incorporate that. First we drop some powder, and after that some curing will take place, and some material is removed, and okay, final shape will be drawn with the help of only by this 3D printing. So we can say that additive manufacturing is layer by layer manufacturing. First we develop first layer, then we go to the second layer, then third layer, and finally our final product will be made. So in this case, first layer, then we can say that the joining of the second layer in the first layer. So process of joining material to make part from 3D model, usually layer on layer, as opposed to subtractive manufacturing and formative manufacturing methodology. So this definition of 3D printing is given by ASTM. ASTM is American Standard of Testing of Material. So I think so this definition of 3D printing is given by, or additive manufacturing is given by this ASTM. So basically, we cannot say that this one is the first layer, and we put just like I have two books. Okay, so layer by layer, I think is it visible to everyone? Visible.
Yes, sir. It's visible, sir.
Okay, so layer by layer means first I keep this book, and another I put this one. Okay, so another third book here, fourth book again, just like this, and I can say that it become additive manufacturing because I layer by layer. So in that case, we can say that if there must be some joining between those layers, only in that case we can say that it is additive manufacturing and the final product is made. So layer by layer with some joining between, with some adhesiveness or some adhesive between the two surfaces, then we can say that either with the help of some laser or some melting, some fusion. So in that case, we can say that it is additive manufacturing. So because additive manufacturing, there are n number of terms we use: rapid prototyping, rapid tooling, or rapid manufacturing, or maybe, but the most common term now we are using is that is 3D printing. So this 3D printing, I think when you say at your institute, even if we say to our DTech students, they will understand, okay, 3D printing. But if you say additive manufacturing, so they may relate it, okay, it may be somewhat advanced manufacturing or advanced machining or something else. But when you say 3D printing, they will definitely understand, okay, 3D printing or layer by layer manufacturing. So these are some synonyms. We can say that additive fabrication, additive processes, additive techniques, additive layer manufacturing or layer manufacturing, normal layer manufacturing, then solid free form fabrication and free form fabrication. So all these are just the synonym of additive manufacturing, depending upon that we are using laser, or we can, in additive manufacturing there may be n number of classification, that okay, the selective laser sintering or selective laser melting, or maybe melting, normal melting. So these are just the synonyms. So 3D printing or additive manufacturing. So in 2D printer, normally in every institute or even in your cabin, you have a 2D printer. We just give the paper and we give the command, either it is Word document or some other document. So the data which you provide them, input, okay, it is printed on this side, and in case of printer it is printed on this side. But as this is, we can say that it is 2D printer, 2D printing, but because we do not have the height. So if we want to add the height, means third dimension. So third dimension is basically this in the third picture, or maybe the fourth picture. Okay, third picture is basically after the fabrication. This is the product where we have the diagram, we have the CAD model, and depending upon our material. So this one is the material. So the input material and the final product is this one with the help of CAD model. Even I think the cost of this I do not know very much, but the normal 3D printer, normal 3D printer means if affordable 3D printer on which you can at least start some kind of research, the cost is approximately 16 to 20,000. Okay, so and I think approximately 1,000 to 1,200 the cost of this spool, wire spool. Okay, metal spool. So if you want to do or want to start some kind of research in this field, in 3D printing, so an institute cannot afford. In my institute, the cost of 3D printer is approximately, we can say that one printer is 30 to 40, maybe approximately more than 45 lakh. And that is the metal printer. But that is very advanced one. But if you want to start the research, so any institute can at least afford a 16,000 printer, and out of that you just need that wire spool of 1,000 rupees, and after that you start. Okay, what will be the input parameter accordingly? What will be the strength, and what? How can we change the parameter? What will be the means speed? X, Y, Z. You want to change, and after that you can find out the final product. Okay. So this will just the starting. So this fourth figure, you simply observe that the final product is maybe manufactured with the help of layer by layer technique. This will the nozzle, the cartridge is somewhere on upper side, and final product means we are providing height or just value of Z in 3D printer, in 3D printing. So this is the difference between 2D and 3D. Now, why additive manufacturing? So I think one second. Okay, fine. So most of you are aware about this diagram. I think so. You already checked at your home this diagram. The diagram is this part basically. Here, this is one hinge we are using on our door, especially. So, what is the procedure to make this door? If we go a conventional way, so in conventional way there are, I think, differently 5 parts. First and second part is this. Third part is this shaft. Fourth part is this closing pin, and fifth part is pin on this side. So you separately develop all these parts, and after that we do the assembly. So we can make this part. So conventional with the conventional way, we can do this part. But if we want to go for additive manufacturing of the same part, then what is the main challenge for us? Main challenge is that it is a direct assembly, and when you put this shaft in between these holes, that part is we can easily develop with the help of additive manufacturing. That part we can easily manufacture. But what is the main thing or a main challenge? Main challenge is how can we maintain a gap between these surface and this shaft. So for that, we already put some powder particle in between that, so that once powder particle, this red one, this gap is filled up with the help of some powder particle. So initially some powder is dropped, and after that this shaft is printed, so that a gap is maintained, and there may be some movement in between these, and finally this part is manufactured. So, but you simply give, once we design the thing, you simply give the command, and after that our product is manufactured with the help of this additive manufacturing. So what are the benefits of this? Fast prototyping. So why we can say that it is fast prototyping? Because I have worked in an automobile company. So in that company, we just draw, first we design the design a automobile, and after that we go for the production. Not the production, but at least we made some kind of prototype with the help of some wood or some other thing, and okay, fine. Then we go for, okay, now start to develop some at least 1 to 2 automobile, so that we can make testing of these equipment. So either it is going to every stage, and every person is conversant with the process. So it will take a lot of time, because first they design the thing, and after that they go to somewhere else in the same company, that okay, we develop the part, now we start to make the prototype. So this was the normal process. But nowadays you make one design, and if it is design is fine, then you just check the design on the computer itself. That was we can also check in the previous time, we can also check the design, and after that we, at that time it was not possible that I give the print command and our product will start to print. No. So for the prototype, I have to go somewhere else to start, give the contract to someone, he will develop the prototype, and after that he give us. But nowadays, if they have the 3D printer, a good quality 3D printer, they can start to develop the part at their plant, and after that they will assemble, okay, this is our prototype, now you may please check. So those prototype may be of we can say that different types. Those may be rough, those may be fine, maybe virtual prototype, or those may be physical prototype. So that is totally depend upon. If it is a virtual prototype, we can say that always, okay, we made the prototype but only on the laptop. We made, if it is physical type prototype, then we made the prototype physically. Either it is rough, okay, this one is the rough prototype. Suppose for example, just this is a pen, and I want to make the prototype of this pen. So the initially I can go two methods. Either it may be rough or it may be accurate. So if it is rough, so maybe the diameter is not 3 to 4 mm. Diameter maybe 3 to 3.5 to 2.5, maybe somewhere else. So that is, we can say that it is rough type of prototype, not the fine prototype. So similarly, the second one is complex geometry. If you make the geometry on computer, you can print that geometry. But if you want to go, okay, I make one complex geometry. There is one example of this, that I have one cuboid and I want to make a cuboid. Maybe in my previous 2 or 3. Okay, one second. This one is one cuboid, and the space is in between this. We fill this space. Okay. The space is filled, but there may be one circle in sphere between this, and this is, or this side, this is closed. This side is also closed. Internally it is hollow, and the space is filled by one surface. That diagram is not possible by conventional method, or that object is not possible with the conventional method, but with the help of 3D printing or rapid prototyping, that product is we can say that definitely possible, because that is layer by layer technique. At that time we need just this layer, and the internally that spherical sphere, the layer of that sphere. Similarly, as we move upward to this side, or we can say that the product is moved toward, product moves downside, nozzle remains at this point, and new layer will be formed, and it will check that whether it is this surface and the internal surface of the sphere. So we can make the complex geometry with the help of additive manufacturing. That will be very easy. Oh, sorry. So multiple material, new material. Okay. So for multiple material, I have one example. I think most of you heard about the functionally graded material. Okay. So those person or those researchers who are working in the this dissimilar alloys, maybe you heard about this thing on friction stir welding of or welding of joining of dissimilar alloy. You want to join aluminium with copper, aluminium with something, some other material. So that we can say that multiple material on the uh, same component. So that is, there is one another term, functionally graded material, FGM. So functionally graded material is that from, if you want to start, suppose we want to start with the help of this nozzle. We want to start, this is steel and this is upper surface is ceramic. So is it possible by conventional method that this bottom surface is of steel and upper surface is of ceramic? So in that case, what things we should consider? So in that case, I can say that conventionally it may be possible because I start with steel and whenever we need the ceramic particle, I change the ceramic. And maybe I will use some kind of adhesive bonding between the two material here and I will join steel with ceramic. That is fine with the conventional method. But with the help of additive manufacturing, what thing we can change, that at this point I need 100% steel and at this point I need 100% ceramic. And if we are talking about this layer here somewhere, so it is 50% steel and 50% ceramic. Similarly, here steel is 99% and steel ceramic is 1%. So the variation between same component, that is possible with the help of additive manufacturing. We simply select the material and we give the command, and after that we can get this type of material. These type of material are basically known as functionally graded material. Somewhere you can check in aerospace industry that this type of material may be used. New material, you can make new material. Definitely you can make that. If you use someone, okay, here I have maybe if you knew about this thing, that there is one process basically. One process means uh, normally the person who is working in sciences side, physics. So this AFM is related to the microscopy, atomic force microscopy. This word is normally used, but for us, for mechanical engineers, AFM is abrasive flow machining. So most of the in this process we use some media in which there is one polymer, one is biocarbon, one is slurries we use for the for the processing of the material. So, but every time if we change, because there are the final media is composition of three material. If I am able to change, there are n number of polymers. I change one polymer and see the effect. What will be the effect of if I am changing the material? So you can check that for the development of AFM media, abrasive flow machining, in the just like in US ultrasonic machining, we use slurry, silicon carbide, aluminum carbide, just like with the mixture of water. Similarly, we use here we use media. So if we change one media, after that, because previously it may be polypropylene, now and you are changing it from polyvinyl chloride. Okay, fine. So no one worked on this. So this is our new material because it is with the combination of some other material. So I made this new material. I can go for some patenting. So that new material can easily be processed because if there is one hydrocarbon or one polymer, the working range most of the time it is equivalent to another hydrocarbon or another polymer. Most of the time, not every time, but most of the time it is equivalent. So if the nozzle is working for one polymer, it will definitely be work for another polymer also. So new material can also be processed with the help of this additive manufacturing. Enhanced performance, you just if you know the design and you convert the design into .stl format and give a command, then okay, you can get the product. Just you will be very conversant with the design and the command. That's it. Low volume. So low volume here for the mass production. That is, we go for conventional industry. But for the low volume product means we develop one part. Suppose, example, we will discuss with the example. One company is manufacturing one part, and especially related to the, we can say that related to the tool. The tool is, with the help of same tool, we can process different material with the help of same tool. I am using the same tool and I can process 100 material, not the 100 workpiece with the same. After that, there may be some design change in the tool. So I need to change only one tool with the help of 3D printing, and that is customized. They give us the design. Otherwise, every time you have to change the die or something else, because most of the time it is powder metallurgy. Okay, with that the tool is made. So what things I need to change the die, but here there is no need to change any kind of die. You just give the command and your tool is developed. So for the low volume production, additive manufacturing is fine. Okay, customization, you can design the product. Here I have one example. Actually, if anyone working in the biomaterial side, so he can definitely be easily understand this thing. Customization is, you know that every person bone size is different. If I am healthy, so maybe my bone size is somewhat larger than some other person, and if someone is not so much healthy or someone is more healthy than me, his bone size is definitely we can say that it is just the difference in fat, skin or something else, but there must be some difference in the bone size also. So in that case, what is the benefit of additive manufacturing? So in that case, we can say that in case of additive manufacturing, we check the bone size first with the help of any CT scan or there may be image. There are different imaging techniques. We check the bone size. After that, we customize our orthopedic implant. So that is one case that with which we can easily understand the thing, that if it is totally depend upon the customization, even the teeth size, because bone is not visible to us, but teeth is visible to everyone. So teeth size is different. For me, it is different, and if someone go for RCT or something else, so they will basically take your design, and after that, okay, you please come after 10 to 15 days, and we will make one cap according to this size. So with the help of additive manufacturing, because that is of ceramic material or maybe steel material or silver or whatever material you want to make, so they take that design, and after that they start to develop the fabrication of that. So with the help of customization, we check the size, and after that we design the same size in our CAD software, and after that we give the print command depending on the material. Which material, if you want to make the cap of or teeth of silver, then we use silver as a material. If you want to make ceramic, can be used. I also kept one slide for that which type of material which we may process with the help of additive manufacturing. So process chain, I think this part is everyone knows this. This is very basic things I am discussing. That the first step is CAD modeling. We do the CAD model. We make the CAD model on the computer using any software, SolidWorks or something else. And after that, this is tessellation. We make different kind of triangles with the joining adjacent triangles. Make complete part with the help of those triangles. Then we start in the third step. We make slicing. The thickness of slicing is also clarifies what type of either we are getting a rough part or we make some accurate type of prototype or part. Okay, and the curing is sometimes we also use laser for curing. Here there is one or two when you do some kind of research, you can also check once the 3D printing is 3D part is developed. After that, because we need just the heat, with the help of laser, we are getting the heat. So maybe some other method. There are some other method by which we are giving this heat treatment type of thing. So that is now the rapid prototyping system, and finally the finishing. Here I am keeping most of the time we study about the post processing. Once the part is developed, then it is post processing. Post processing is normally, if it is suppose plastic part, then we go for finishing operation, because in plastic part, even when we go for some kind of casing of our mobile cover, mobile covers, so at that time you feel that there are some burrs. So that is removal, because those are plastic part. You cannot say that, okay, now go for the heat treatment. So post processing is involved, either it is heat treatment or some kind of burr removal or some kind of finishing operation. So all these collectively we can say that it is post processing. So once the part is made, after that we will check that either it is fine, dimensions are fine or not. If dimensions are fine, then we can say that okay, now it is our final prototype. If dimensions are not fine, there may be some feedback. So we will give the feedback to the programmer, and not to the programmer, obviously to us, but now we make the modification according to the feedback. So this is our drawback here. So drawback not related to the dimension, that may be related to the strength, because your nozzle speed define many things. Suppose everything is accurate, but here once during the slicing process, you keep the nozzle speed very high. After that, the curing time, we are not giving the proper curing time. So finally, when we get the final product, the strength is not up to mark. So in that case, the drawback is also involved. There may be dimensional, not the dimension, it is not dimensionally accurate. There may be some strength issue, there may be some other kind of issue. We give the feedback, product come to again the first stage, and finally it repeated, where there may be some kind of problem. If it is related to the curing, we increase the curing time. So this is the process of additive manufacturing. So first is the development of CAD model, the first step, then developing of .stl file or tessellation. So this is our second step. Then slicing is our third step. That tool path generation, how the tool is moved. So that is our fourth step, that involves the movement of this. This is our plate which rotate rotate or revolve. Accordingly, this laser comes and either it is dropped here depending upon the angle between this. If we are not interested to make the drop of angle here, the rays, we want to we may change the angle. So this is revolving type. It may revolve in any direction depending upon where we want to drop our laser or where we want curing. So that is our tool path generation. The printing will take place then post processing. So this one is the process chain related to CAD. So this is somewhat previously which we studied, that first is the CAD model, this one, then surface model we develop. So you can, this thing maybe in next slide we will discuss this thing, that this is our CAD model on some desktop or some laptop. 1 second. So when we start to surface model, so the lines which you check here, there are different lines. So these lines are depending upon the thickness of the layer. Okay. So when we make this type of model, .stl convert or known as tessellation, so it is basically how precisely we are adding. If anything, maybe in the next slide we will discuss. Okay. So that is related to the circle, and if we are making smaller triangle, the accuracy is fine. If we are making larger triangle, accuracy is down, something related to this. So this is our slicing process or layer model, and keeping one layer over above, this is our support structure basically. This is our product. Support structure is this one, because we cannot put it somewhere else. At that time, if the support structure, maybe we can say that the width is so that the material which is at the edge, that it cannot be dropped down. Okay, so it will be in intact position layer by layer. If suppose we keep the support structure, okay, fine. We keep the support structure. I am making some layer. So basically, this is the layer, and this layer is normally of plastic part and molten material. So if it is molten material, there are maybe two type of forces which are acting at the edge. So one is gravitational force and another one is surface tension. So in that case, definitely material try to go in downward position. So better that we keep one layer here, and the support structure is somewhere larger than this. So material remain in intact form. So this is our 3D printer, and finally, so here basically one thing is missing. The post processing is finally we can get the same product, but after the printing. So STL file means standard tessellation language or standard triangle language. So it is basically STL has derived from stereolithography, because when we heard about additive manufacturing, most of us heard about 3D printing or okay, stereolithography. Those are basically stereolithography, those work in electronics especially. So even in mechanical also stereolithography everyone heard. So STL is a boundary representation model of an approximation idea of the product. So suppose this is our product. So here we can say that up to this part, up to this, or we can say this. This surface is flat. So if this surface is flat, everything is fine, and this is uniform. But after that, this part, the width is decreases. So at that time, here triangle size, I think it doesn't matter because it is uniform up to here. But as we move from this point to this point, the triangle size decreases because as we increase the number of triangles in varying length, if the length is uniform, then it's fine. If length is varying, then we have to reduce the length triangle size to get more uniform, more fine idea. So the process of tilting a surface with more or one or more geometric shape, there will be no overlap. So that is the tessellation. Tessellation, the best example is we can say that honeycomb or in tiled floor. So there will be no gap. That gap is already filled. If we see this, there will be no gap conventionally, but finally we can say that the gap is filled up with some kind of cement or something else. So that is tiled floor is one example of tessellation. This honeycomb, that is also another kind of example of tessellation. This is first example is we can say that artificial, and this is natural. So nature is also involved in this tessellation process and fire, or we can say that 3D printing, because when we see this honeycomb, so you may check this thing that honeycomb is not they basically develop it with time. They initially drop some material and finally that first layer is formed, then second layer is formed. So similarly, they develop this final structure that is also one kind of layer by layer structure with existence in the nature. So this thing, this is one thing that there are three images. In this first image, the triangle size is very high. A triangle size is large. Here, third. So triangle size is very small. Or we can say that in first, there are very few triangles. These are also very high, but as compared to the third one, there are very few triangles. But as we move from first to third, our accuracy increased. So tessellation is totally dependent upon the number of triangles, or the accuracy is dependent upon number of triangles which we are using for this approximation or for approximate idea of the result. So as we move from first to third, accuracy is definitely increased. So we can say that with the increase in the number of triangle, our accuracy is increased. So in this way also, this is our product which we want to make. So initially we take this, the second one, and if we increase the number of triangles, the final shape we can observe this one. So this is one example. So information in STL format. Once we make some design on SolidWorks, we have to convert it into .stl format. And suppose you make one design and you want to convert it. There are n number of options to convert it from SolidWorks to .stl format. So here there are we need four things basically. If there are three vertices, so where our vertices lies, first thing, and this is the normal vector, whether it is outward or inward. So for this in this format, this is ASCII format. So American Standard of Computer Information Interchange, I think so. This will be the American Standard of Code Information Interchange. I think this will be the name. So here we want to know where this normal vector lies from the upward side. What will be the angle? So that is given in the first thing. So if it is inward, then this n This is the normal vector. This exists somewhere to the downside. If it is outward, it is to the upper side, and the angle value of the angle is also given. Now P1, P2, and P3, these are the vertices. So the value of the vertices where it lies, so that is given. So in this way, the only this is the one triangle. So similarly, there are n number of triangles, and this format is given accordingly, and we will process it on our 3D printer. So the maximum STL deviation, actually one more thing, I will wind up, not the wind up, but basically along with this additive manufacturing, maybe I will around 7.5 or 7.10. I want to finish the additive manufacturing, and after that I also want to show you some two things basically. Those are basically related to the persons who are working for the research. Okay, so that's why when it is around 7.5 or 7.10, you please let me know so that I can move to that part, and now I start to cover up things at a faster pace. So STL deviation, how can we, what is the maximum value of the deviation? So we can say that this is the triangle. We cannot say that the actual value, this is the chord or this is the circle. So the actual value in case of triangle, that never be possible. If we make a smaller triangle, then in that case, one second. Okay. So if I want to make a triangle, so in that case, I start to make this, but still there is some deviation value. So in case of triangle, you cannot achieve the rectangular portion. Rectangular portion. For that, if you want to decrease the size of triangle, still there may be some gap. So in this case, at the larger, if we make some kind of amplification, so this is the deviation. So this value, this deviation is known as STL deviation. So it is the chord height, and it is recommended to insert tolerance between this is 0.01 to 0.001 mm. So in case of angle, okay, so in case of angle, so suppose there are two triangles, the center portion of this triangle, this one and this one, and this angle, that is known as angle tolerance. The maximum angle between the normal vector of two consecutive triangles, that is the angle tolerance. So slicing, I'm going for the faster pace now. Okay, slicing is basically the CAD model. Okay, so every time we have to put one layer. If the thickness of the layer is large, suppose in the first case, if thickness of the layer is large, our surface quality or our product quality definitely be deteriorated. But if we increase, if we decrease the layer thickness, now these are the thin layer. So if we decrease the layer thickness or quality, product quality, we cannot say, we cannot say that our product, this will be the final product, our product is equal to this, but at least it is equivalent to this. But in this case, you can check the difference. So when the layer thickness, or you use thick layer for the development, and now we are using thin layer for the development of this prototype. So we can say that this one may be somewhat nearby to this, not exactly this, but at least somewhat nearby this. And if we do some kind of finishing operation, maybe we can say that on an we cannot get the ideal one, but nearby one to this. So one is uniform slicing. So classification on the basis of layer thickness. So one is uniform slicing, another one is adaptive slicing. Uniform slicing, this is the case of uniform slicing. So first, every time a uniform layer is used. So if it is a rectangle from this to this, then it's fine. There will be no issue. But as maybe I use the same picture of DOM in 3 dimension in my 2 to 3 slide back. So if it is a rectangle, then it's fine. But if it is not a rectangle, some portion is of uniform value, another portion is of variable thickness or variable DOM size or semicircular section. So semi-spherical basically. So in that case, if we make smaller thickness, so we can get a better structure rather than this one. Because in this, once the final structure is made, then now the next step is to remove the extra material. So our rework is increased. So we basically opt adaptive slicing if that product is non-uniform type. Now the horizontal slicing, and in this case, one second now. Hello. मैं थोड़ी देर में करता हूँ, मेरा लेक्चर चल रहा है अभी. ओके ओके. So if it is horizontal slicing, so we have one is our substrate, or we can say that surface to support the structure. We put different layers horizontally. So after the finishing, our final shape is this one. Okay, so that is horizontal slicing. Now conformal slicing. Conformal slicing, our substrate is this, and we radially or with the help with some curve, we are adding some surface. So that is conformal slicing. So final product is this, and I think you already this conformal slicing is already existed in nature. This is also a conformal layer in cabbage, conformal layer in our onion. We check this thing. So these are the conformal slicing. So classification are basically wet for polymerization, material jetting, binder jetting, material extrusion, sheet lamination, powder bed fusion, directed energy deposition. So for the first wet, approximately 40, actually the sequence, if I'm giving first, second, third, fourth, fifth, sixth, and seventh. So this is low energy. First is low energy process or lowest energy process, and seventh is highest energy process. So these are distributed according from low to high energy. So first, in the first process, we may use the energy of approximately 40 milliwatt, and in the last we may use the energy of 6,000 kilowatt. Okay, so in this way, these things are processes are varied, and these are as per the ASTM. Okay, so in wet here one word is missing, wet photopolymerization. So here this one is the laser, these lines, these are the support structure, this product we want to manufacture, and this is basically one resin is here, and that is photo activated. Okay, so once the laser is dropped at any point, that part is because material is photopolymer, so that part is hardened. So we want that this portion be hardened, and okay, it will be cured maybe after 3 to 4 days. So we are basically interested to cure this portion. So we drop the laser only that portion. So with the help of photopolymeric action, the curing will take place. Okay. So in material jetting, so in this case, this one is the material, These are the drops of the material which are dropped from this nozzle, and here are ultraviolet light. So the material which we want to cure, the part, these are dropped on that portion only. Suppose, for example, we have some cement. Okay, every part, every place we have cement here, and now we add some water from this nozzle. Particular location, I want to add this portion. I add the water only this portion, and I start to cure this. So finally, the remaining portion, this one, cement is in powder form, we can remove that portion, and the final product, cemented cement with water along with proper curing, we can get. So the binder jetting in which, sorry, in which liquid bonding agent is selectively deposited to join powder particle. So material extrusion. So here there are two type of material, two type of wire spool is used. So this is the actual material we want to develop the product, with the help of which we want to develop the product, and the black wire with the help. One second. Um, um, Actually, I'm audible. Actually, my HOD called me, so it is very obvious that I have to pick the call of HOD. So,
Yes, sir, you are audible, sir. Please go ahead.
So material extrusion, most of the time, material extrusion process is used. So one second, I am going for the. So the black wire is for the support structure for the part, and this red one is for the part which we want to basically manufacture with the material with which we want to manufacture the part. So the both is used, and where we want material, it is basically dispensed with this nozzle. So that is known as material extrusion process. So sheet lamination is also known as we can say that laser object manufacturing. Laser object manufacturing is long basically. So here this is layer by layer structure, first thing. And along with that, we have one spool. Because of layer by layer structure, first layer is of different size, second layer is of different, third may be of different size. So similarly, but every time we have to cut from where we want to cut, that is with the help of the laser cutting, first thing. But the example is remains same, that if I keep one book on the another book, at that time we cannot say that it is a layer manufacturing, but at least we have some bonding agent between two surfaces, then we can say that it is a sheet lamination or laser object manufacturing long. If there is some bonding between these two material, if there is some bonding, no, bonding is activated after some curing. If we are giving some temperature, after that curing will start take place. Otherwise, on the roll, it is one material layer on the another material layer, it is on hard condition. But when we give the temperature, curing will start take place. The materials start to diffuse in between one another. So in that case, it is sheet lamination. So it is 7:10 already. So I am going a little faster. So powder bed fusion in which we use thermal energy to fuse resin together with the help of the rotation of this and with this laser. Okay, direct deposition, either it is okay. In the previous powder bed deposition, you heard about selective laser sintering, selective laser melting, injection molding, selective injection molding. So all these are the type of powder bed deposition. When you heard about electron beam or lens process, laser process, so these are direct energy deposition processes. So in this way, this the last two or three process normally we are not using on commercial level. We are just using these processes in research level, or most of the time in India we are using only the 3D printer. Either it is a metal 3D printer, where somewhere in India, I think a very countable position, countable location we can see this metal 3D printer, but normally those plastic 3D printer everywhere. And so these are the category of the material. So polymer and composites, metal, ceramic, biomaterial, and construction. Because you may be, because everyone nowadays on Instagram, so you may see that there are a person who put the picture. Okay, these houses are made by 3D printing. They use some concrete and cements mixture and start to make the structure. And okay, within 3 days we make this structure. You can easily check the 3D structure of house on YouTube or some Instagram. Okay, so now there are different applications. So this thing I have basically suggested, because teeth teeth of every person are different. The size is different. So if it is related to the customized size, every time we have to make the design accordingly. So these muscles or things are different. Even we are using nowadays bio inks for the development of soft tissues, skin, liver, heart, something like this. So those are related to the biomaterial field. So food items, one example is maybe few days back I go to some shop and they simply, sir, we can also make picture of your son on cake. So that is also one kind of things developing nowadays. So food 3D printing, then bridge. These are some turbine structure, and these are aeronautical parts. So all these, there are n number of applications of additive manufacturing. Even during COVID, not during COVID, but we start to develop one article at that time, that what are the different applications of 3D printing in COVID. So at that time we already means written one article that there may be different applications of 3D printing in COVID, either mask or something else. So Shri Hari sir also one of the co-author of that paper. So that this case study, so that I will definitely discuss. So this case study, you can check that this is basically one structure, and when you see it, this structure is maybe some metallic structure, but so how can anyone suggest? Can anyone tell me that which type of printer we use to develop this metallic structure? Anyone? Okay. So normally for the development of this metallic structure, we may use a metal 3D printer normally. Okay. So in one case, you can check that it is this circle size. Circle is octahedron. The circle space is octahedron. And in the second case, these are cubic or square structure. So if we change the structure, what will be the effect on strength? What will be the effect on some other? Actually, it is basically topological. Topological ordered open cells, porous iron scaffold. So we've made porous structure, but we do not have this metallic 3D printer. So I just took this picture from one of research paper. So in this one, first is CAD model is developed. Then we make 3D printed template of this CAD model. We make the 3D printed template. Then this 3D printing template we fill the material. The 3D printing is used to develop this structure. After that, we fill the same structure with some metallic particle. Once the metallic particle is filled, metallic particle means we filled with metal, binder, everything. And maybe you can use the plastic material, this polymer material, which act as a binder also. So once it is in molten position, so after filling the metal in this, so we started with some sintering process, and the sintering or heating is taken up with the help of microwave sintering. So if it is microwave sintering, it is plastic part, so it may get evaporated, and finally we can get this structure. But instead of this CAD model, here we are using rectangular or square holes. So if we use some octahedron or some other shape, some rectangular shape type of structure, so definitely property differs. So now the last thing is journal selection. So normally most of the person, when we communicate one article in any journal, we basically check, okay, normally even my PhD student says, sir, can we get this article to be published in 1.5 months or 2 months? Because my PhD submission is nearby. So I want to complete it, or otherwise extra fees we have to deposit it to the institute. So first thing is, how can we check the journal selection or review time? So most of person are very well aware of this thing. So now discard. So in case of Springer, I am just taking the example of IGMT journal. So think it is visible to everyone. So any article, if we check this article, so here at the end, it is written that article is received on 2nd of April, then accepted on 31st December, published in 28th of Jan. Most of the journal nowadays start to write, suppose if we go on this, so submission to the first decision, 9 days. They have mentioned this thing, 9 days, but don't fall in this. 9 days is that if they send a decision that your manuscript is not fit for our journal, that is this time, 9 days. Otherwise, they will take 2 to 3 months. Okay, so but okay, fine. If they are not interested to publish our article, then we can go for some other journal. So in case of Springer, most of the time it is given at the end. But now my suggestion is, I have one suggestion here, that once you go for any journal means any, either it is a Springer, or I am also showing you some journal, CIRP, International Journal of Manufacturing. So this is related in case of elsewhere. Most of the time, this piece is for the open access. So we are not going to open access. So any article, okay, I've taken this article. So received on 29th of July, revised on 4th of December. So 29th, it will take approximately 3 to 4 months, because at least the person will take 1 month to revise. So it will take this. So on 5th of accepted within 1 month after the revision. So but now either it is a case of elsewhere or Sage or Springer, any journal. Never fall for the article which you see here, but try to find any article which is written by Indian author. Okay, because many things change when the author is Indian. So better to check how much time they will take to publish the article written by an Indian author. So maybe I'm writing here. Sorry, not here. Here I'm writing. Okay. So I think available online 15 July 2022 version of record. They missed the thing. But there may be some article history is always there. Why it is not here? Do not know exactly, but most of the time it is available article history in case of elsewhere journal. So all issues. Full. Okay, this is article history. On 6th February, it is received, revised on 31st of May, accepted on 28th of June, available 8th of July. So this history is written for every, but try to find out an Indian author in this journal. No, not in this, but any journal. And check out 2 to 3 authors, and then you will find out that how much time they will take for review process. So in this case, because you have to check the things, because most of the time if they provide you, in case of Springer, they will provide you a median time. Okay, we are taking 1,000 of articles per year, and out of that the median time is this for the first version or from first to final. But the things are varied from author to author, editor to editor, and number of factors exist. So first thing, this you have to check. Now the copyright of table and figure, because most of us are interested to publish their article, and maybe few days back we faced some problem regarding the figures. So here, if suppose this one is the article, and I want to cite in my review article, I want to cite this figure. So I have two methods. Either I have to make the same figure using some Canva or something else, okay, or in some cases I want to cite their result, just like if there is some, okay, in my review article I want to use this figure. This is figure 9. I want to use this figure. So then simply get rights and content. So you have to take copyright. Most of us simply write that give the citation of this paper. We have taken our art, this figure from this paper, but did not take any type of copyright. And still, when they ask you have used some third party figure, and we simply select in the copyright, we have to submit. That we select no. But because you are citing some other work,
Sir.
especially in table and figure, so you please take this.
Dr. Neeraj sir, sorry for interruption, sir. A kind reminder, sir. This is 7:25, sir.
Oh, okay.
Yeah.
So
you have 4 minutes.
just give me 2 minutes.
Yeah, yeah.
Okay.
Go ahead,
So here I want to use it in a journal. So reuse in a journal or magazine. I am not here I will select publisher because I am taking the copyright on behalf of some publisher in which I have communicated my article, what to use some figure or table. My number of figures, I am taking one figure. My format is both. I am the author of this article. No, I will be translating. No, my currency is. Yes, sorry, but we are unable to process your order has not been saved. Again. So maybe there is a. I have to make a. Okay, my format is this. No. There may be some issue with the website, but if we go with this way, so there are 0 charges, there will be no copyright fees, and you can apply the copyright. They will send you the copyright. You can use that figure in your article after taking the copyright. That is free of cost. So from my side, sorry, from my side, it's over. Thank you. So if you have any query related to anything, you can ask me now, or you can send me a mail. That will be no issue from my side.
Dear participants, if you have any queries, please raise.
Sir, good evening, sir. This is R.S. Kiran from SVP Engineering College, Visakhapatnam.
Yes.
Sir, can you suggest any simplified book of additive manufacturing, sir?
Book of?
Additive manufacturing by Indian author.
Okay.
Which has got more number of narrative figures.
Actually, better if rather than book, if you follow this NPTEL
Courses. Okay.
NPTEL notes, that will be better because it is a composition of 3 to 4 notes. And whenever we go for because for the students it's also fine. And whenever we go for some kind of interview, at that time you will definitely find, even in entrance exam, you will find all the questions are either asked or related to those NPTEL, because that is the crux of 4 to 5 books.
Okay, sir. We are hearing about this 4D printers nowadays, sir. In which book is that mentioned very clearly, sir?
Which process?
In which textbook is that available? 4D printers, 4.5D printers.
Okay, so I think edited books are in edited book it is fine, but there will be no conventional book related to 4D or 5D printing, because this 4D or 5D printing are on the research scale nowadays, not the convention or commercialized 4D or 5D. We are working on 4D if time is variable, so that is fine.
Yes, sir.
Yes.
Okay, sir. Yes, sir. Thank you, sir. Thank you.
Sir, actually we did hit already 7:30, and actually other resource person is in line, sir, is already waiting. So I request we'll be in touch with you through mail, sir. All the queries, all the participants, if you have any query, you can mail him. He will be available.
We will drop sir's mail ID.
Yes, yes.
Yeah, I'm dropping my mail ID in the chat box. If you have any query or you want to have any question related to additive manufacturing or somewhere related to the research, so you can ask me, no issue.
Sure, sir. Now I request Dr. Kelly Durga Prasad to summarize the session and yeah, close the current session. Thank you.
Yeah, thank you, Dubba. On behalf of the organizers and participants, I would like to extend our sincere gratitude to Dr. Neeraj Sharma for delivering such an insightful and enriching lecture on the basics and the working principles of additive manufacturing. And thank you for your presentation, sir, which was both engaging and informative. And thank you for throwing some light on the journal publications also, because we are having a lot of doubt on the time period of the journals. So today we have got some idea, and we also came to know about the copyrights, how to apply for a copyright, because every time we are trying to draw the entire diagrams. So we have got some idea on how to get a copyright. And thank you so much, sir. And we are looking forward to more such enlightening sessions in the future. Thank you very much, sir.
Yeah.
Thank you, sir. Okay, sir, I'm leaving now.
Yeah.
Thank you,
Yeah.
everyone.
Thank you, sir.
Thank you
all
so
the
much, sir. Neeraj, sir.
all the participants, we will have a breath of 2 minutes, and we will start after 2 minutes. Stay
Santosh,
tuned.
the next
Yeah.
resource person, Ravikiran sir, has already joined.
Yes, yes. Yeah, yeah. Thank you for the information. We'll start after 2 minutes, sir.
Ravikiran sir will join in a couple of minutes. Just now, this previous session has completed.
No problem, Sri.
Yeah.
Yeah.